Heat can travel from one place to another in three principal ways: conduction, convection, and radiation. Sometimes more than one way occurs at the same time. In this lesson, we consider each of these. First, conduction. Why do your bare feet feel colder when you stand on tile than on wood of the same temperature? It's because tile is a better heat conductor than wood. Tile conducts heat from your feet faster than wood does. There'd be even less conduction if you stepped on a wool rug. So we see that conduction is heat transfer by molecular and electron collisions within a substance. Conduction occurs when fast-moving molecules on the surface of your feet bump into slower-moving molecules in the tile or wood surface. Heat energy flows faster from your feet to the colder tile than to the colder wood. So different materials conduct heat at different rates. Materials that quickly conduct heat are conductors. Good conductors include metals of all kinds. The good conductivity of metals has to do with their electrons, which in metals are freer than in wood. Free electrons about metal atoms can drift throughout the metal and transfer energy by collisions to other electrons or atoms. In contrast, electrons in wood are not free to wander throughout the wood. The atoms in wood are fixed in place and grab onto their electrons, which don't easily migrate from atom to atom. So wood conducts heat very slowly. We say metals are conductors, and materials such as wood are insulators. Good insulators also include air, wool, plastic foam, and even glass. Lil holds her wine glass by its insulating glass stem, which lessens heat transfer from her hand to the wine. The snow patterns on this roof show areas of conduction and insulation. Bare parts show where heat from the inside has leaked through the roof and melted the snow. In the previous lesson, we discussed John walking harmlessly with bare feet on red-hot coals. The conductivity of wood is low, even red-hot wood. Very little heat is conducted from the coals to his feet as long as he keeps stepping. Would he walk across hot coals of metal? No way. Firewalking is safe only if the hot coals have low conductivity. And even then, you take your chance that a piece of hot coal doesn't get stuck between your toes. Ouch! Let's talk about the second way that heat can transfer from one location to another: convection. Convection is heat transfer in a fluid by means of currents in the fluid. By now you know that a fluid is either a liquid or a gas, both of which can flow. And you've got to know something else about molecules in a fluid. They're in perpetual motion. That's right, perpetual motion. Molecules of air you put in your auto tires last year were moving then and are moving now, continually providing air pressure in the tires. If no leakage of air and no external energy changes occurred during the past year, the air molecules in the tire have the same average kinetic energy they had previously. Internal energy of the air in the tire has not changed. No molecules of air got tired. They still move. Perpetual motion is the way it is. Yum to nature's way. Here we see a couple of common examples of convection. Heated air circulates in the home, and heated water circulates in a pan on a hot stove. Energy transfers from one location to another due to currents in the fluid. This J-shaped tube at the San Francisco Exploratorium shows convection in action. The tip is heated and produces convection currents that are nicely visible due to deflection of light by water of different temperatures. A similar thing happens with warmed air by a candle flame. Now you can see why you can hold your fingers on either side of the flame without being burned. Air is a poor conductor, so very little heat is conducted from the flame to your fingers on the side. The heated air is buoyed upward, away from your fingers, which is convection. And a third way that heat transfers is radiation. Radiation, heat transfer by means of electromagnetic waves. There's something else you've got to know about materials. All materials continually emit electromagnetic waves of energy. That's right, everything radiates. Here we see a radio antenna, a fireplace, and an incandescent bulb. All are radiating electromagnetic waves of energy, which we call radiant energy. The source of most radiant energy is vibrating electrons. We'll discuss this much more in future lessons. For now, you should know that everything contains vibrating electrons, and all vibrating electrons emit waves of energy carried in vibrating electric and magnetic fields. Some waves are long, some are short. The wavelength of electromagnetic waves is related to the vibrational frequency of the electrons that emit the waves. To clarify this idea, note the little girl setting a rope into vibration, which produces waves along the rope. The more rapidly she vibrates her end of the rope, that is, the higher the frequency of vibration, the shorter the waves. In a similar way, low-frequency electron vibrations produce long electromagnetic waves. High-frequency vibration produces waves of shorter wavelength. There's a lot more I want to tell you about radiant energy, and I'll defer that to the next screencast. In the meantime, I want to leave you with a question. First, you know that you can place your hand briefly inside a hot oven without harm. But you'll burn your hand if you touch the inside of the metal oven. So my question is, what does this tell you about the relative conductivities of air and metal? Until next time, good radiant energy.